Look at the observable universe, and you see persistent structures everywhere: atoms, stars, cells. But the deepest open problem in physics is why these stable patterns manage to exist at all, rather than instantly dissolving back into formless thermal noise. Standard physical frameworks lack a mechanical answer for this. They often treat the existence of stable entities either as a given starting condition or as a statistical side effect of complex interactions. In 2026, physicist Peter Baldwin published a paper proposing a strict mechanical solution, a framework called General Emergence Mechanics, or GEM. Baldwin's model treats the observable universe itself as a dynamical coherence shell, a mathematically defined boundary where physical laws operate. Within this framework, emergence is stripped of its philosophical baggage. Things exist because specific, deterministic mathematical rules prevent them from breaking apart. Whether a structure holds together or collapses depends on three coupled dynamical axes governing this shell: depth, stiffness, and relaxation time. Under GEM, the formation of a stable entity requires no special forces. Existence is simply a measurable property of persistence. To understand how this works, we have to look at the underlying substrate of GEM, the vacuum structure defined by modal theory and the global coherence framework. In this model, the vacuum of space is an active field anchored at a highly specific preferred phase minimum, exactly 255 degrees. This free energy landscape visualizes the phase field. It maps a three-dimensional topological space where the preferred 255-degree minimum forms a deep primary basin directly in the center of the grid. The shape of this space is dictated by equation 1, the effective shell free energy. This mathematical backbone locks the lowest energy state, the bottom of the basin, to the precise coordinate of 17 pi over 12 radians, which equals 255 degrees. A secondary equation, an exploratory orbifold bias ansatz, introduces a 24-fold sectorization. This creates distinct scalloped ridges that radiate outward from that central point, subtly texturing the primary basin. This specific topography is what Baldwin calls the coherent shell. It defines the literal physical boundary where stable structures can form and survive. By treating the vacuum as a shaped basin, emergence physically shifts from an abstract concept into a quantifiable geometry. When a localized event or particle distorts the space field, its survival depends on how it interacts with the topography of the shell. The first defining axis is shell depth. This cross-section of the potential well illustrates depth as a vertical measurement. It represents the total energy barrier required for a perturbation to completely escape the shell's basin and dissolve. The second axis is effective local stiffness. As the walls of the basin compress and grow steeper, we see stiffness at work. Defined by equation 10, it dictates the shell's immediate elastic resistance when subjected to a structural load or phase distortion. But depth and stiffness only define a static geometry. They describe the shape of the trap, but they lack the element of time and motion. To solve this limitation, the framework incorporates the Rayleigh dissipation functional, shown here as equation 3. This equation introduces the third critical axis, effective viscosity. Viscosity models how a perturbed state frictionally and irreversibly relaxes back down toward the preferred minimum. The math dictates that any configuration's ability to persist as a recognizable entity is entirely governed by its interaction with these three specific variables. This brings us to the nature of time itself. In GEM, time is not a pre-existing background dimension in which events happen. Instead, it emerges from a fundamental mechanical question. Exactly how does a distorted phase field physically return to equilibrium? If the shell's viscosity drops to 0, as shown in this animation, a displacement snaps back instantaneously. Without friction, there is only a sequence of isolated reversible points, leaving no temporal thickness. Conversely, if viscosity approaches infinity, the wave is frozen at its peak. The shell remains permanently distorted, relaxation stops, and the unfolding of time effectively freezes. But with finite positive viscosity, the system experiences a delay, a characteristic recovery time. This forces the shell to retain the posture of a distortion for a specific duration. This delay creates a window where the shell's current configuration is still physically influenced by its previous state. This recovery interval is what generates the distinction between before and after. We experience the instantaneous local posture of the shell as the present. The past consists of distortions that have already relaxed enough to leave a lasting record in the shell's configuration, while the future is the gradient of dynamically favored relaxation paths the shell is already pulling toward. In this framework, the unidirectional arrow of time is the lived signature of finite viscosity relaxation inside the coherent shell. By defining how the shell recovers, we also define the fundamental mechanical filter for reality within GEM. This time series graph visualizes the persistence condition. For any entity to exist, its coherence lifetime must exceed the shell's recovery time, represented here by the dotted line. If a transient fluctuation, like the first waveform here, decays before crossing that threshold, it fails the inequality and dissolves. But a configuration that outlasts the characteristic recovery time locks in. It passes the threshold and stabilizes. This threshold directly maps onto quantum mechanics, particularly regarding the behavior of virtual particles. Virtual particles are not a different category of matter. They are transient phase distortions that simply fail the persistence test. Because of the shell's high stiffness, these brief excitations are violently driven back to the vacuum minimum before they can acquire a stable identity. Based on this, GEM formally classifies the stability of any configuration into distinct categories. A stable state robustly occupies a deep minimum. A metastable state occupies a shallow local minimum. It can persist for long periods, but is separated by a finite barrier from a lower, more stable basin. Finally, transient or non-persistent states are those that immediately decay upon generation. The coherent shell acts as a universal mechanical filter, definitively separating the virtual from the real based entirely on mathematically derived persistence. This framework is not isolated to the quantum vacuum. Because persistence relies on mechanics rather than specific materials, GEM is entirely substrate independent. As shown in this split-screen diagram, the exact same phase field math translates directly into applied engineering. Depth, stiffness, and relaxation time map perfectly to material, biological, and computational models. In materials science, yield energy equates to depth, elastic resistance is stiffness, and long-term creep under stress is viscosity. In biology, cellular stress responses and chemical buffering represent systems actively maintaining their local structure near a stable phase basin before an irreversible transition occurs. We can even see this applied computationally. The Franke V5 to V7 models serve as an engineered proof of concept for GEM, treating conversational states as phase fields. These models implement a selective persistence regime. The architecture continuously measures the coherence of the current state. When the system detects a high-tension, unstable state, it triggers costly, high-stiffness corrective processing, mathematically forcing the state back into a stable basin. Conversely, stable, high-coherent states are handled with low-expenditure processing. By only applying full computational stiffness when the system detects a threat to its persistence threshold, the model achieved up to a 37% reduction in token usage without a drop in output quality. GEM provides a unified, transferable mechanical language across all systems. In this framework, the complex appearance of emergence resolves into the measurable mechanics of persistence within a coherent supporting shell.